Good morning, everybody, and welcome to our, well, it's not our last session, but last session of the week on graphing, where we do more examples on step 4 because we need them. We need to see all the things that we need to see, and we have not done enough examples on step 4 just yet. Alrighty, so let me just get I made notes of which examples I would like to do. Let me just get that out here. So what did we do last time? We saw a polynomial where I do step 4, find the concavity, meaning I have to find the second derivative, and we classified inflection points. And we said, if we remember, let's remember, while someone confirms that in the chat they can both see and hear me, I'll remember what inflection points were. Inflection points. It's very similar to critical points in that I need the now second derivative to be 0, or, I don't need to write or, the second derivative is undefined. And I need it to be a point. So my function has to be defined at that point. Now, it's a little more technical than that, but for our purposes, it's going to be sufficient to just say that. And there's a third one that the critical point classification does not have, in that the concavity must change as I cross over it. So we saw last time, if I quickly copy it, we had a 1 and a 3, and we had some detail, but essentially the second derivative went from plus 0 minus 0 plus, bending up to bending down to bending up. And I had y values for both of those. It was a polynomial anyway, so I knew it was defined. And we had a change in the bend, in the concavity every time. But there are examples, and not even complicated examples, that show that it doesn't have to be an inflection point every time, even though it's an important point, even though it's in my table, even though the function's defined there, the bend isn't always going to change. So let's have a very simple example. I think it's fairly simple. X minus 1. Anything that I can just do transformations on to understand is pretty simple. So I don't need this technical root, but I just want to show that I can do it and what it looks like. So of course, on the way to the second derivative, I need to find the first derivative, little chain rule, 4x minus 1 cubed times 1, which I guess I can write it, but I don't need to look at it to move forward to the second derivative. I then have 12x minus 1 squared, of course, times 1 again, which I don't need to look at. So there's my second derivative, not complicated at all. I'll do it over here. Second derivative is clearly 0 when x equals 1, and the second derivative is undefined. Never, it's a polynomial. So I get my potential inflection points, and there's one of them. I don't know if it's an inflection point yet, right? Because I've only checked the first part. But it's definitely a potential inflection point. I list everything, maybe a 12, maybe an x minus 1. Why are there brackets? I don't know, and there's another one. And together they give me the second derivative. 12 is always positive. X minus 1 is 0 when x is 1. Goes from negative to positive. Makes the second derivative 0. Same for this one. They are copies. Now I have two negatives and no negatives. I'm bending up and I'm bending up. Now, this diagram is just for me to remind myself the bend. It doesn't mean it's a full turn. And in fact, it isn't. So I'll just write over here. My function is concave up everywhere because I don't have to exclude 1 because it's defined there. I have a y value. The y value happens to be 0. So I have a point. I have it as a potential inflection point, but the bend doesn't change. Now, by way of one single transformation, I can very quickly graph this, of course. It is based on my basic function. X to the 4 is just like a U shape. Whoops, no, I didn't even shift it. Wow. Shift it to the right. U shape there at 1. Like that. It helps if I make sound effects. Makes it smoother. So you see, it does actually make a full turn through 1. So the left side is concave up and the right side is concave up, and they attach and make a full turn. So I need that for it to be an inflection point, I need the bend to actually change. So there is no inflection point. It has no inflection point. Okay. So for the increasing decreasing behavior, a critical point is one that comes out of my check for the first derivative, of course. And if there's a point, it's good. It's a critical point. I don't care if it's increasing and decreasing or changing or anything. I don't care. If there's a point and it comes out of the check of the derivative, it's good. But the inflection point requires a little more. Comes out of the second derivative check, there is a point, but the bend has to change. Otherwise, it's not technically called an inflection point. It's still important to me. It's still in my table. I still take note of it. I treat it just like any other point. I don't discriminate. But somewhere someone decided, nope, we're not calling that guy an inflection point. Even though in terms of how I use these points, I really don't discriminate at all. They're always important. All right, so in a way, the inflection points are easier. We don't have that many little things in examples that we did for step 3, I feel. But correct me if I'm wrong, of course. Let's do another example. We don't need these examples to be super complicated. We are not done even after this. We have to practice putting all the information together. That still is coming next week. So the discussion isn't done. We'll have more examples. Now, here I need to, of course, go through the first derivative in order to get to my second derivative. First derivative, we have done before. This is the same example I've used previously. So I'll just copy it. Hopefully that looks familiar. And if not, just trust me. That is the derivative. You have to do the quotient rule. You have to clean up the quotient rule. And this is what we get. Now I have to do the derivative on this. Now many people go, quotient rule, absolutely. I see it. It's a rational function. There's nothing wrong with that. Let's do it over here. And of course, then I have the bottom one squared. So then I have to the power of 4. Derivative of the top times the bottom minus the top times the derivative of the bottom. And then I have to simplify that because I have a reason to simplify. This times 0 means that the term is irrelevant. I have a negative 4 and one of the brackets cancel to leave 3 of them at the bottom. Nothing wrong with that. But know your options. Know your options. I have fancier properties that might be applicable. I could see this as 2 times x plus 1 to the negative 2. That means I can avoid the quotient rule, but I have to use the chain rule. So this is an OR. So I could use that approach instead and say, okay, chain rule, negative 4 x plus 1 to the negative 3. I don't love negative exponents moving forward, so I move it to the appropriate side, and you see I get the same thing. Some people love the quotient rule. I don't want to stand between you and your love of the quotient rule. That's okay. But know that you have options. And the chain rule is another option. Whichever one really gets me to simplify safely, honestly. That's my priority here. I don't want to make a mistake in simplification because I'm going to use that simplified version moving forward. So regardless of how you get it, I get the same thing, right? So the second derivative is 0 when. Second derivative is undefined when. First one, 0. Let's see if we've learned something. The second derivative, whichever one, they're the same, right? It is 0 when. For which x values will that second derivative function equal 0? This is your moment. Seize it. Never. See how we've learned? It's good. It's good. Never. Because there are no x's in the numerator, and only the numerator can make a fraction 0. It's undefined, clearly when x is negative 1. So, because these examples are fairly small, I get, again, just one contender. It's negative 1. Now, of course, in isolation, this doesn't really give me a clear impression of the graph. But if we look back and remember we have done steps 1 and 2 for this function, it's not that bad. It's a little unsatisfying if I do all this work and I still don't know what the graph looks like. I'd like to know. But this step alone is not sufficient. So negative 4 is always negative. X plus 1 is 0 when x is negative 1. It's in the denominator, so it makes the second derivatives undefined. It's going to go negative to positive, and all these guys are the same. I could merge them together. If you're comfortable doing that, go right ahead. But the simpler I make each of these pieces, the easier it is. I have 4 negatives, and I have 1 negative. So I bend up, I bend down. Let's write the sentences. I did not write my sentences here, did I? Oh well, it's over. F is, I did actually, no I did, I remember. Concave up on negative infinity to negative 1. Infinity always gets a round bracket. Does negative 1 get a round bracket or a square bracket? That is my question. Round bracket or a square bracket? These are things you're going to have to ask yourself. And if you're watching in YouTube, you can still answer. There is a chat box. You are not exempt from these questions. Round bracket or a square bracket? I want to include it. I really do. I want to include as much as I can. But I am referring to the original function. And the original function up here is not happy with negative 1. It's undefined at x equal to negative 1. So I can't include an x value that doesn't have a point. I'd love to, but I can't. So for that reason, it is not a square bracket. I wanted to, but it is not. That is not even a pretty round bracket. Come on. Eh. So I have to know why I'm doing things, and then, well, I need to know what I'm doing and why I'm doing it. Concave down, I need to know the reason. Concave down, -1 to infinity, obviously. Again, for the same reason, I can't include that -1 as much as I'd love to. Can't be done. It is not allowed because the sentence, the statement, refers to points of the graph, really, in terms of the x values. Okay. Now, let's remember what came from steps 2 and 3. I really had a lot of information. We knew it was going this way, and this way, and this way, and this way, and all the increasing, decreasing information told me that. The information I got now totally fits with this, because I'm going to have to bend up to the left of course, I have to update these arrows. I didn't know how they fit. I have to bend up on the left side of -1, and I have to bend down on the right side of -1. So everything agrees with the information I would have gotten up to that point. So if you make a little mistake, maybe in your simplification of your function, something gets mixed up, you get information and it just doesn't match up. That tells you then something went wrong. All the pieces of the puzzle, everything has to agree and eventually lead me to the graph. There can't be contradicting pieces of information. So I do have a little bit of a check that if there are pieces of information, if I look at all the steps that contradict each other, that means I probably made a mistake somewhere. Finding it, well, that's another question. That's an issue on its own. But at least there's an indication that something went wrong. Oh, we're not done there, right? We're not done. We have this x equal to -1. Is it an inflection point or not? Let's write it out like this. Inflection point, ooh, that's ugly, at x equal to -1, question marks. I need to know. It's definitely a contender. It's the only contender that came out of my list. Is it an inflection point, yay or nay? Those are your two choices, yay or nay. YouTube is very quiet. I don't know. No, your choices were yay or nay. Those were the only choices. I'm sorry. And you have to know why, right? You have to know why, because you can't guess 50-50 and hope you're right. Why is it not an inflection point? Why? That's important. Can't guess. I need to know. Because we have said it before, I know. It's a contender. The concavity is changing, but there is no y value. There's no y value. There's no point to call it any point, regardless of an inflection point. There is no point. So you have to know all the requirements to be called those things. Sometimes they ask you, what's the inflection point? What's the critical point? Sometimes they don't. Regardless, you have to write these sentences at the bottom. They're very important. Make sure you get your intervals and your brackets right. That's where people lose marks very quickly. Alrighty, we're moving along. Maybe too fast. Let's go to one we've seen before in terms of the other steps. So it's nice to sort of fill in more and more steps of the same function. That way we can put it together and have an idea of the graph. Now, that's my function. Exponential component. I don't really know what this graph is going to look like. I know I'm going to lose symmetry. I know that. Very likely. It's probably some asymptotes in there, but who knows? We got some information out of steps 2 and 3. I don't know if we did step 2 on this one. Whatever, doesn't matter. You might have to just do step 4 in isolation and just be okay with the fact that you don't know what it looks like. Okay. So we did do the first derivative. We got this guy. So now we have to do the second derivative. Take the derivative of this. So clearly a product rule. Derivative of the first times the second plus the first times the derivative of the second. Now those both look like e to the x, but the first one I took the derivative, and the second one I didn't. The derivative just happens to be the same. You'd be surprised how quickly people think, oh, we just copy the same one down. He's not doing the product rule, he's doing something else. No, it's always one of those properties. I can factor out an e to the x, and I have a 1 plus 1 plus x, 2 plus x. That wasn't so bad, not at all. Out of this, I get the second derivative equaling 0, check. Second derivative, undefined, check. Second derivative equaling 0, when one of these two guys equals 0. Well, from the bracket, I definitely get negative 2. And e to the x is 0 when? Same questions coming up, and that's how we learn. Important questions, underestimated how important they are. E to the x is 0 when? It is 0 never. How do I know? I picture the graph. It's always above the x-axis. So it's not guessing. It's not memorizing. I literally read it off the graph. That wasn't really what we were talking about, but they're both defined. Everything's good. It's not going to be undefined ever either. So I get one contender. That's not bad. It's better than nothing, I guess. Mark it off here, negative 2. Then I'm going to list everything. I have an e to the x. I have a 2 plus x, and they combine to give me my second derivative. E to the x, we just said, is always positive. 2 plus x is 0 when x is negative 2. It's multiplication to make the second derivative 0. It's going to go, double check, negative to positive. I don't guess. I don't memorize. I just do it very quickly. You have to be sure. So I have a positive and a negative, negative. Positive and positive, positive. Bending down, bending up. Again, not a full bend necessarily. I don't know what's going to happen. I'm just reminding myself what the plus and the minus means. Okay. Let's write our sentences. Actually, let's do it over here. F is concave up on certainly negative 2 to infinity. Infinity always gets a round bracket. Negative 2. What kind of bracket does it get? So in the process of writing these sentences, I am sort of answering the inflection point question, sort of. I'm finishing the inflection point question at the same time. Inflection, there's sort of a hand-in-hand situation here. Points at it. Oh, no one answered me yet. Does negative 2 get a round bracket or a square bracket? That was my question. Still complete silence from the 6 people in YouTube. Take part. See how much we've learned in the few days by just taking part. Square bracket, because I'm referencing the original function. Actually, in this case, yeah, they're all happy with all x values. but the original function is the one I'm making a statement about, and it is defined everywhere. The y value will be negative 2 over e squared, whatever that is, I don't know, don't really care, it exists. That's the most important thing. When I go to graphing, sure, I need to put the y values in their relative places, but right now I just care about existence. So that also means that, yeah, inflection point. Because it came out of my check, there is a point, concavity changes, all three conditions are met. And let's finish the sentences here. Concave down, of course, on negative infinity to negative 2. If I include it once, I'll include it everywhere. All right, so now it's a little unfulfilling here. I'd like to see the graph and how could this possibly happen? Sure, we could do that because we have some information from prior examples. EGI, okay. So I'll zoom in a little bit here. We had a critical point at negative 1, if you look back, remember, and we saw that it was going to make a little cup there. If you did step 2, and I don't think we did step 2 on this one, in combination with step 3, we would have a horizontal asymptote over there, and just going off to infinity on the other side. We would have a y-intercept of 0, and that's pretty much what we have, right? Increasing on the right side of negative 1, actually decreasing on the left, increasing on the right. Okay, so somehow we have to come down to that turning point and up. Okay, it's fine. The concavity now tells me exactly how this shape looks. Let's do the right side first. I need to clean this up a little bit, right? So I don't have the symmetry, right? Don't try and balance this perfectly. It's going to be a little tight on the right side, a little steep rather. That's okay. And on the left, see bending up? No, it's bending up through to negative 2. Let's put that over here. And if you actually calculate the y values, the inflection point sits a little lower. Not necessarily I can't remember if it's halfway. I don't think it's perfectly halfway, but it's in between this turning point and the x-axis. Of course, it has to be. There's no other way, right? So let me just clean this up a little bit. So now I'm going to turn at my critical point. Oops, no, that's too fast turning. This side of when I can't see my hand is deceptively hard. I'm going to turn up, or bend up rather, all the way through. And then I'm going to change in the way I bend to bend down towards the horizontal asymptote. And if you look at the derivatives, none of it was really complicated. I didn't have a lot of potential critical or inflection points. My table wasn't big, the derivatives were easy to simplify, everything was pretty straightforward in terms of complexity. Yet I get more interesting graphs. I get graphs that have an asymptote on one side, and a turning point, and changing in the bend. It's interesting stuff. So I like this middle ground, this exponential component type function is the sweet spot. Now I can't just ask you this type, I have to mix it up, unfortunately. Otherwise it'll get boring. But this is sort of the sweet spot. Not too easy. I don't know what the graph looks like. I'm going to have to do the analysis to know. Even if one of the pieces up here, even if one of the pieces changed, if I change that to an x squared or I change it to an e to the negative x, the graph changes drastically. So there's some interesting stuff within this type of function as well. And it's something worth doing. Like, I want to see how the pieces fit together because I don't know what the answer is beforehand. If I did this guy, I already know what the answer is, right? It's the transformation of x to the 4. If I do this rational function, I already know what that answer looks like. And based on asymptotes, I can pretty much guess it, which you may have done in pre-calculus. But these guys, I have no idea what they look like. It's an interesting discovery. Well, it is for me anyway. All right, that gets us halfway, and that was really all I wanted to do. Let's see what else we can do. Let's see. Actually, yeah, I'm going to stop there with step 4. I think that's sufficient. I just want to have a little overview again because it's important. It helps me anyway. So my steps. Warm-up step. Not given enough attention. Identify the function. Y-intercept. Oops. I want to write Y-identify. Y-intercept, and so on. If you don't want to identify the function, leave a little bit of mystery. That's fine too. I don't really mind. Then we really got into the big steps. Asymptotic behavior. Asymptotic behavior. Then we looked at increasing, decreasing behavior. Increasing, decreasing behavior. And we looked at concavity now, which I think might have been easier than increasing, decreasing behavior. Anyway. So notice how these are following each other, apart from the first one. When I looked at the asymptotic behavior properties, I looked at the function itself. Let's call it f. When I look at increasing, decreasing behavior, it's all about the derivative. Now, I am trying to make statements and conclusions about the original function, but I get that information from the derivative. When I look at concavity, I look at the second derivative. So I essentially look at everything I can from the function itself. Well, not absolutely everything. Everything I need to, really. Some books look at symmetry and all kinds of stuff. I don't really care. It's just wasted effort. I want to keep it as clean and efficient as possible. Then after I've examined the function, got some stuff out of that, then I move on to the derivative. Get everything I can out of that. Then I take the derivative of that derivative, get everything out of that. And luckily, past that, doesn't really help me too much. It's not very useful after that for just getting the shape of the graph and the basic properties. There is another step that is very much, what's the word? Not underappreciated, but easily neglected and not given as much importance as the others. And that is just the actual graphing of the function. It's not trivial to put all this information together and then be able to sketch the graph. You can get all the information, but actually putting it together is deceptively difficult sometimes. So I want to do a couple of things. We need to just pay attention to step 5, as if someone else has done steps 1, step 2, 3, and 4. They've done it for me. I don't need to worry about it. They give me all the information that I need. Can I put everything together? That is a very important step. Now, I don't have the problem book open. I'm going to have to quickly open it. And I can't speak and open files for some reason. It's because my push to talk button is the Alt key, and I can't alt and double click stuff. Okay, so where are we here? We're graphing. 9E. What page could that possibly be? Who knows? Let's guess 60. Just not a bad guess. Sketch a graph. So it's a question just like the others. So I know you're focused on the second midterm, which is Monday. Surprise. But this whole graphing thing is on the following midterm, where essentially it's not hard to predict. There's going to be one question on step 2, one question on step 3, one question on step 4, and a question where it looks like, where are we now? It's going to look like things like this, where I give you the key information. Can you put it together and have a rough idea of what the graph looks like? As if you did all this yourself. You see here that I got some limits that comes. So the first parts here come from step 2. Then I have some derivative information. Now, it's not completely all the detail of the table because I don't really need it. I only need to use the bottom row. I don't need to see all the pieces because someone else has done this for me. And then the second derivative table results are here as well. Can we put all this together? So at the very least, I just want to do one, or maybe we shouldn't. Maybe we should leave it. We have time next week. Maybe we'll do it next week and focus on the midterm because this is the last time we see each other. Now that I think about it, let me do that instead. So let's just pause it here and realize that there is a little more to do. That even though I have all the information, it's not trivial. It's not super easy to put it all together. So I do need to practice that on its own as well. And then towards the end of next week, we will take a function and do everything in addition to putting it together, just from the start to finish, all the questions there are. So there is some more to do. We're not fully done in terms of our practice, but let's just pause here, pause this discussion, and just talk about the midterm and double check the schedule. Is the midterm on Monday? No one really asked me any midterm questions, so I guess everyone's okay. Where are we now? Yeah, it's Monday. Yeah, midterm 2. Let's have a look what is on that thing. We can be in denial, but it's still coming. Okay, so our first midterm stopped at rates of change, right? So, as the website would also say, the midterm is going to be on really everything about derivatives, to be honest here. That would be topic 4, where we start with a limit definition. That's really all I need to know out of topic 4. Then the derivative properties, the basic ones, and the chain rule has its own topic number, and then exponential and log functions, and we are not doing topic 8. We're not doing trigonometric functions. So it's very straightforward, really. It's easy to prepare for. You just have to practice enough variety. Can you do the limit definition? That's obviously one question. It's not a shock here what's coming. Can you use the limit definition to find a derivative? And of course, we keep that function fairly straightforward so that the limit doesn't get ridiculous. Can you find the derivative in a lot of detail, like we did at the start, saying which property you're using at every step, all the detail? Do you know every property that is being used every line. And then I usually have a question just for product rule and quotient rule, because sometimes when I think about the chain rule and everything, there are options, right? You have options. You actually can avoid these sometimes. Actually, no, I don't need to make a new page. For example, like I said, the quotient rule, if I have f of x, whatever, I don't even know, x squared plus 1, I always write that function, I don't know why, x minus 3, I don't need to use the quotient rule. I could look at it like this. That was an ugly plus y, and have x minus 3 to the negative 1. And then it's a product rule in combination with the chain rule. So I can use this and find the derivative of the first, which is 2x, times the second, because I don't care about simplification, right? I don't care about how messy my answer looks. I can take this route. Derivative of the first times the second, plus the first times the derivative of the second, which is a little chain rule. And just leave it there. It's perfectly fine. So I have a question usually that says specifically use the quotient rule first, so that you don't have an option for which way to go. Specifically use the product rule first, just so I can test those. Do you know them? And then, of course, the chain rule really is in combination with other things, right? If I ask for the derivative of these exponential and log functions, of course, other properties are there. The chain rule's everywhere almost. I can't really avoid and isolate these things. So 6 and 7 are very much mixed. Do you know your natural log and exponential functions? Do you know the general base ones? Just all derivatives, all the time. That's pretty much the essence of midterm number 2. But do you have any questions about the midterm? I don't know what else to say. It's very straightforward. Can you find derivatives in all possible ways? And do you know the functions? Look at our examples. Uh, I think our examples are very representative of what you need to know, and then it's just for you to decide, oh, I need to go practice general log functions a little bit more than the others. Or, oh, I need to really make sure I understand which properties are used when, and be able to write them down in detail. Whichever sticky point you may have, you can then go and practice that. Are there any questions? Let's see where I have a schedule here, right? What's our schedule saying? I do keep having Sunday morning Q&As. No one ever shows up. I don't know if I even need to bother. But I still do them. So we've done concavity here. We have, yeah, see, we have more sessions next week. Graphing, and then there's a video where you sort of have to just go and work through stuff from start to finish. I have a video on each type of function where I slowly, well, it's slow because you can pause it, work through every step for each type, then put it all together, everything. To really show you for which kinds of functions, which steps are a little bit more involved, and other types of functions have easier steps and things to watch out for and so on. So we still have pretty much the whole next week to do that, and we'll slowly move on. And then there's another midterm in the end, and so fast. It'll happen so fast that second half you won't even know, because I've laid the foundation early, and now after we're done with graphing, things are going to fall into place very nicely. I'm just buying time to see if there are any questions, but obviously there are not. So we will end our discussion here. Maybe I see you before the midterm, maybe I only see you next Tuesday. Regardless, I hope your studying goes well. Until then.